So this is linear algebra, right? And we are doing problems from Hoffman and Kunze. Problems. So this is 1.1. I'll say 1.1.7. Okay, let us see. So this is just about prove that every subfield of the field of complex numbers contains every rational number, right? So let's write the question. Every subfield of the let us just write of C contains Q. So tell me, what have you tried?
Yes, sir.
Yeah. So is this the question?
Yes, sir.
Okay. So tell me what you have tried.
No, I don't know how to start writing this proof.
Okay. No question. Yeah. So so you see, first thing is every field has the identity, right?
Yes, sir.
So that's the first thing that you should use. Maybe every field has multiplicative identity and additive identity, right? Has identity. So now, if you're starting with the complex numbers and you're taking a subfield, you know what subfield is?
Yes, sir.
Right?
Subset which follows.
Yes, a subset which is a field, okay, using the same operations as in the bigger field. Okay. So now, because we are using the same operations, what will be the multiplicative identity of F? Okay. So what is because we know it is unique, what is the multiplicative identity of F? So
One, sir.
it is the same one, right? It is the same one as it was for C. Why? Because it works and because it's unique. So there is no question, right? So it is the one only. It is one. It is the complex number one. Okay. Now from here, can you show that every rational number is there in F, right? We want to show that every rational number P by Q is there in F. Try it. Think for a few minutes and see. Maybe you can try to first show every natural number is there, then every integer is there, then you can show it.
Okay, sir. Okay, sir. Sir, can we suppose a number x which is in the form of p by q, and for every p by q, the multiplicative inverse q by p such that multiplication of both is equal to 1.
Okay.
And hence every p by q.
Why? If P by Q is in F, then Q by P is in F. This I agree. But why should P by Q be in F from what you have said? Okay. Think. Yeah. It's easy.
Okay, sir. Every complex number we can write in the form p by q. Hence, can we give arguments like this?
Every complex number can be written in the form
Complex number upon 1. which is one multiplicative identity.
Okay. So
So it becomes in P by Q form.
no, I do not understand the sentence. The sentence, English sentence, I'm not understanding. Try to say that. Yeah. Think you can say.
Uh, for every complex number
Hmm. Okay.
P, we can write P upon 1.
For every complex number p. Okay. So all right. So for every complex number, I will say z, not p. Okay. Yeah. This
Okay.
z is equal to z upon 1. Okay.
It is in form of P by Q. So it is also that.
It is in form p by q. After that, but why should it be there in f? There's no reason, right? Okay. And why will any complex number be there? That's not correct. Can you show that 2 is in there? So 2 is in. Hmm? We have shown that 1 is there because f has multiplicative identity. Similarly, 0 is there. So we have shown that 1 and 0 are in f because field should have multiplicative and additive identity, and they has to be same as the one for the original field. Can you show me why 2 should be there in f? Just think, why should 2 be there in f?
So 1 plus 1, I mean,
Correct.
1 plus
Correct.
1 equal to
Yeah.
2 by
Because 1 is there, so 1 plus 1 has to be there because the field is closed under addition, right? It's closed. Binary operation means that, right? It's closed. So 2 is there. So now can you show that n is a subset of f natural numbers?
Yes, sir.
Correct. Now show that z is there. Try to show minus 1 is there.
Yes, yes, sir. Uh, not remember. Sir, sir, we shown one is one belongs to F,
Hmm.
so and 0 belongs to F.
Yes.
Then obviously minus 1 belongs to F
Why?
because 1 plus minus 1 is equal to 0.
Okay, but you should say that additive inverse of 1 has to be there, right? Field, every
Yes,
element has an additive. You have to say that. Otherwise, you are saying the correct thing, but you have to say it so that it follows from the rules. You have to say it like that. That you have to write field has additive. Every element has an additive inverse, and so minus 1 is there, so z is there. Okay, now show that p by q is there. So now give start with a p by q. Start with a p by q and show that this is in f. Okay, simple thing.
Sir, we have shown 2 belongs to F. Then each is field, then there must exist its multiplicative inverse 1 by 2.
Yes, right. And in that way, 1 by n is there, and so m by n is also there. Correct. Done. So it's easy, right? It's a very easy question. You can try to prove a generalization of this. You can show this following thing. Every field. So you can do this for homework. It's very, very similar, but build on the things you have done. So every field F contains either Q or ZP or some prime. Okay. So here C is not in the picture. You also saw that in the last problem we did not really use C too much. Okay. But anyways, you can think about it. So what the spirit of this question is that every field at the bottom has a basic field in a very simple language, right? Every field at the bottom has a basic field, and on top of that, a more complicated field is put. Okay. Why it is put and so on, that you can think, that's up to you. Later on, you will study these things properly. But for now, you can prove this fact. And what else I was saying to say? And this is going to be very useful. Okay, there is, after you do a little bit of linear algebra, if you study field theory, you will see that this concept that C is a vector space over Q. So C has Q, right? That you have actually proved more. You have proved that every subfield of C has Q. So C has Q, right? So it means that C is a vector space over Q. If you know the definition of vector space, you will know that. If you don't know that, then you will read it soon. So that is not a problem. But what happens is that this interpretation of one field over the other as vector spaces becomes very fruitful. It allows you to use linear algebra in field theory, and that's very, very useful. So anyways, we will move. Okay. Please try this question and you can. All right. So now let me look at the next question and let me see if we need to do it or if you can give it a try. Yes, I think now you can do number 8 on your own. Okay, you should try it because now you know the method, right? So there is no need to do number 8, right? I just wanted to look at problem number 6. Have you tried problem number 6?
Yes, sir, I have tried. I mean, I tried with it for like two homogeneous system of two unknowns have the same solution. Then they are equivalent. I took like two equations. A1 x plus
right, correct. So you look at two equations.
b1 x plus b2 y equal to 0.
Right. And they are saying that if they have the same solution, then they are equivalent. All right. So before we talk about this thing, so one thing you already know, right? That I'm just asking this myself actually. That if this is ax equal to b, okay, and if I apply a row operation, right, then this system, this is a new system, right? This becomes a new system.
Yes,
some row operation. This again is a column vector, and this is again similar kind of thing. Yeah, nothing changes. So that is then basically then these two have the same solution, right? So and these two are called equivalent by definition, right? When you do a row operation, the new system you get is called equivalent. Okay? So equivalent systems have the same solutions that everybody knows, that you know. Here they are saying if the systems are equivalent, no, I mean, if they have the same solution, then they are equivalent. Right? So given that given same solution set, show equivalence. Right. So yeah, so I suppose this is not very interesting. This is a simple problem because it's 2 by 2, right? You can just do all the kids work. So I will just you may have done it in certain way, but see if you like this method. So this one, when you reduce, right? When you reduce the system, then okay, same solution, then they are equivalent, right? So when you reduce the system, then what kind of uh, mm, yeah, how can you write the most general? You cannot write it at once, I suppose. You get something like this, and the other situation can be you get some a prime and you get 0 0, right? And of course the other situation is right. So the other situation will be that the first column is 0, okay? Then this can also be 0, right? After reducing the some things, or if this is 0 and this is 1. So after simplifying, these are the only things that you can get, right?
Sir, is it possible that third null matrix? How is it possible?
Yes, null matrix is possible, right? If you start with null matrix, then you get null matrix, right? Yeah, you are
Okay.
right. You are right in the sense that if you don't start with null matrix, you don't get null matrix, right? So yeah,
Yes, sir.
that is correct, correct. If you don't start with null matrix, you won't get null matrix. So this can only happen. This can only happen if the original matrix is if the original if and only if the original matrix is null. Okay?
Yes, sir.
Yeah. So these are the yeah. So when you have a column and then it's a pivot column, then you can take the entire column, you can make 0 other than that, and otherwise you can go forward, right? Or if there is no pivot, then that column yeah, it can have zeros, or it can also have non-zero entries, right? That can happen, right? So these are the only situations, right? And then the solution set of this is 0 0, right? And what we just want to say that if they have the same solution set, then they are equivalent, right? So what will be the solution set of the second type?
X equal to 0. X.
Um, uh, no, yeah, x equal to minus a and y equal to no, sorry. So y can be y, right? And x will be minus a prime y, correct? Right?
Yes, sir.
This is what it is, right? And this you can just write more elegantly, maybe. Yeah, I don't know. You can write it like no, sorry, that does not make sense. Okay. So let us just write it like this, and then you can simplify that. But yeah, and this one will be yeah. So how do you read the solution for this? Yeah, so here x can be anything, right? You can take x to be x, and then y will be equal to, right? Y will be equal to 0, of course. Yeah, this is this, right?
Yes, sir.
So you see, for yeah, so basically for every solution set, for every type of solution, you are getting a unique row reduced echelon form. Sorry, I mean you are getting a unique equivalent form, right? Like these, right? So basically, um, if the solution is this, yeah, if the solution is this, it means that the system is equivalent to this, right? If the solution is
Yes, sir.
this, then it means that this system is equivalent to this, right? So basically, if the solution set is given, then you can tell what is the equivalence class of that system. Okay? So if two solutions are not same, so for example, if uh, uh, then they are yeah. So basically, yeah, I mean, if they are not equivalent, so if they are not equivalent, then the solutions will be different, right? So if one of them is equivalent, say if a matrix A, matrix B, and if B is equivalent to this and A is equivalent to this, then they are not equivalent because these two are not equivalent. These two are not equivalent. Then their solutions will also be not equivalent. Okay. So in this case, it happens, but it does not happen in general, I think, right? So given, yeah, that is something which we can think later because we will come to all that row reduced echelon form and all that. But given two no, so given two different row reduced, okay, maybe it is. So we can first of all we can just talk about when a full system row reduced different, right? Then the solution are also different. Row reduced echelon form is they are inequivalent. Yeah, I think this is also true um, in general, but I'll not making any claim right now. Okay. Yeah. We can think about this later. That becomes a bit tricky. Yeah. So we can think about that later. Okay. So tell me then what other questions should try. Because that when you do road with this one form then.
I didn't try the next exercise.
Okay. Yeah.
I just read one time.
Okay. So you have read the second section number 3.
Second. Yes, sir.
Okay. So you have read the section. So let us try the problems then. Right. No reason to wait. Let us try the problems. Yeah. You have not tried then. Which one should we try? Huh. Yeah. Okay. Maybe what I will do is I will give you maybe 10 minutes break. and why don't you try the first 3 questions, right?
Okay, sir.
Yeah, try the
Okay.
first 3 questions, and then maybe in 10 minutes we can get an idea of this, and then we can discuss. So I'm ending the meeting, and then in 10 minutes